In the previous segment, we defined sound pressure level from the sound intensity level and all, and because we said that pressure is a easier thing to measure. But then we also said that in this segment we will be talking about different frequency zones in which these things can be considered or discussed. And then this is important because as in one of the segments I had told that our ear is a very rugged kind of sensor or transducer, which can in fact sense signals over 10 octaves. Okay. So, we will talk about what an octave is and all those things over a very large range of frequencies. In fact, from 20 hertz to 20 kilohertz it can sense. Now, so what it means is if the sound pressure level is varying at 20 cycles per second, then also we can hear it. And similarly, if it's oscillating at a very high frequency around 20 kilohertz, obviously it's not the same for all ages. So when the person is younger, they can hear even very high frequencies. On the net you can actually see there are tests. You can run the sound which changes frequency from very high frequency to low frequency to check which frequency you are able to listen from the higher side and from the lower side. You can take that test. So with age that changes the range, but on an average they say 20 hertz to 20 kilohertz we can hear. And similarly, while speaking, for male voice around from around 125 hertz to 4000 hertz we produce, and for female voices around 250 hertz to 8000 hertz are produced. Depending on person to person it varies, but that's the average. Now, because these are the variations over frequencies, so we should also talk about the sound pressure levels, not only in terms of the amplitude which tells us about the energy and all, but also the distribution of that energy over frequency. And that brings us to the topic of frequency bands. That means we always represent the total energy in terms of bands of frequency. If you remember, while we were talking about continuous distribution of anything, it's not a well posed question to ask what is the energy at a particular frequency. We should always ask in a band, and that is how it has been done is some bands have been predefined. Okay, and we always measure the energy of a given sound signal in those bands. Okay, so those are like bins, and because our ear is sensitive in a logarithmic way, as I had mentioned in the previous lecture, so these bins are also created in a logarithmic sense, in the sense the first bin. So, suppose one bin contains the energy from say 16 hertz to 32 hertz. Then the second bin will not contain the energy from 32 to 48, but 32 to 64. Okay. So what I mean is, see, 16 to 32 is one bin. Suppose I put all the energy which are coming there, but the next bin is not a linear. I mean the difference is not same, but it's the ratio is same. So it's 64. So these are hertz, suppose. Okay. So all the energy which are coming there, I'll put there. So like that, in the next bin it should be 64 to 128 hertz. So like that, I'll create bins and I'll collect all the energies which are coming into those bins, and if I plot them as a histogram, that basically will give me idea about what is the energy distribution of any sound field or sound signal at a particular instant of time. Okay. So now For this, what has been done is, if you see here, I am just using this, suppose is upper limit of the frequency. If this is the lower level of the frequency, then I can call it the center frequency, something. So like that, and then the relationship is that Fu is always 2 times Fl, and if when that happens, we call that it's an octave. Okay, the upper frequency is 2 times the lower frequency, and the center frequency is the geometric mean of the upper and the lower. Okay, so that means from lower to the center, if you want to come, so you have to do Fc is equal to, say, Fl 2 raised to half. Similarly, again, if you multiply Fc into 2 raised to half, you will come to Fu. So that's how you will move, and this, if this is the way to create the bins, so those bins are called octave band what do I call bins. Okay, octave band distribution is the distribution when you plot them. Okay, and generally on a diagram, these center frequencies are shown. Okay, for example, you will show 16, 32, 64, 128, and like that you will draw. And see here, we have I have taken these segments of equal size, okay, on the x-axis. That means we are plotting them on a log scale, and that's why though we are doubling the frequency, we are still maintaining the same width of the segment on the x-axis. And then the lower, so every such band will have a certain width, and that will start from 16 over 2. So this will be 16 over root 2, and this will be 16 into root 2. Similarly, this will be 32 over root 2, and that will be 32 times root 2. So that is how the bands will be, and the energies will be shown in those bands. So like that. So that's how you represent the spectrum of the power spectrum of any audio signal, the sound signal. Okay, so and then there is one more way. If you want a finer resolution to see that, okay, I'm not happy with these thick bins, and then you can go to 1/3 octave band maybe. So in that case, what happens is, instead of this F U to Fl will be 2 raised to 1/3. Okay, and then again this remains the same, the center frequency. So that means you can calculate from one step to the other. That means Fc will be F lower times 2 raised to 1/6. So like that, if you move, you can go to other thing, the next frequency levels. But then what happens in that is, generally you will have finer bins, so you can get a finer distribution of the energy across the frequencies. So that it's just that, nothing else. Okay, so octave or 1/3 octave. Then what else do I have to say? Yeah, so these are sometimes called constant percentage bandwidth, because they define this bandwidth of nth, like I said, 1/3 filter or 1 octave filter. So that you can actually define as Fu minus Fl over the central frequency, and that you represent as a percentage. Okay, so that will always be 2 raised to n over 2 minus 2 raised to minus n over 2 divided by so that into 100. Okay, so that for octave band it comes to be 70.7% for 1 octave, and it comes to be 23.16% in 1/3 octave band. Okay, so because this is a constant number, when you take this Fu minus Fl and take the percentage with respect to the central frequency, this percentage remain constant at any frequency that you pick, and that is why they call it constant percentage bandwidth filter. And and this is how you define the bandwidth of a particular octave band. Then anything else I wanted to say? Yeah, then now we are in a position to talk about the dBA. You remember I was when I was showing you that picture, this picture here, instead of dB, dBA was mentioned. So now we are in a position to talk about what is dBA against what is dB. So that we will discuss in the next segment. See you in the next segment.